So, in chapters 10 and 11, we introduced the basics of organic synthesis. And what we did there was we really focused on how to construct a molecule with the correct carbon skeleton, and then we also focused on how to convert one functional group into another. Now that we've gained experience with even more reactions, we are going to continue our discussion of organic synthesis and explore some of the higher level topics that will allow us to synthesize some more elaborate target molecules. Now, in chapter 21, much of our focus is going to be geared towards things that are helpful to consider when synthesis calls for the formation of a new carbon-carbon bond. Carbon-carbon bonds typically form between carbon atoms with opposite charges, and unfortunately, we are often faced with the challenge of forming these bonds between carbon atoms that are initially of like charge. So, we're going to begin with a strategy to accomplish this. And then we're going to focus on clues in a target molecule that help us determine the types of carbon-carbon bond forming reactions that we should think about in a synthesis. We are also going to consider ways to tackle a synthesis where these kinds of clues don't exist. Another focus of this chapter is our ways to circumvent synthetic traps. Um, Specifically, we're going to look at the use of selective reagents to carry out reactions that target one functional group over another. And we're also going to discuss strategies for keeping functional groups intact by using protecting groups. Now, this is a really short chapter. We just have two sections. And so this screencast will be on the first section of the chapter 21.1, and then the next screencast will cover the second section. So in chapter 11, we stress the importance of reactions that can alter the carbon skeleton, and specifically reactions that form carbon-carbon bonds. So far, about 20 carbon-carbon bond forming reactions have been presented. So when a synthesis calls for the formation of a carbon-carbon bond, how do we know which of these reactions might be appropriate to use? Once we decide on a particular carbon-carbon bond forming reaction to use, what other issues should we consider when we start to convert starting materials into the necessary precursors for that reaction? And so that's a lot of what this first section is going to focus on. So in chapter 7, we learned that a bond can form between two atoms when one atom bears a partial or full negative charge, and that means it's electron rich, right, or a nucleophile, and the other atom bears a partial or full positive charge, making it electron poor or an electrophile. And so, kind of as we said over and over, positives and negatives are attracted to each other. And so, to form a bond, a lot of times we use this attraction. We have something that's negative and something that's positive or partially positive. Now, just kind of that general idea that we're using these different charges is really applicable to a lot of the reactions that we've looked at, including these carbon-carbon bond forming reactions. And so when we look at this example, this is one we've looked at before. You can see where this is negatively charged, and that's partially positively charged. And these electrons are going to come, they're going to attack this carbon, right? And that chloride is going to be the leaving group. And so the new carbon-carbon bond we formed here is shown right here. Okay. Now, because carbon-carbon bond forming reactions normally involve these oppositely charged carbon atoms, a problem arises when we want to form a bond between two carbon atoms bearing the same charge or similar charges. So if we look in equation 21.2, if we were to put these two things in a reaction vessel, there would not be any reaction because there's not going to be any bond that readily forms here because these atoms here both have similar charges. So one of the things that we're interested in is there any way that we could maybe change those charges? And so one way to do this is to form a bond between two carbon atoms of a like charge is to carry out a separate reaction that reverses the charge of polarity at one of the carbons. And so that carbon becomes more electron rich. Now, reversing a charge at a particular atom is a strategy called an Umpolung. And so when we talk about this particular word, it's a German term and it means polarity reversal. Right? And so this is a common practice in organic chemistry. And so we've already encountered some reactions that where an Umpolung takes place. So we, from chapter 20, right, learn that we could convert an alkyl halide, shown here, into an organometallic species, such as a Grignard reagent. And I really want to point out, look, this is partially positive here in this alkyl halide, and when it turns into a Grignard reagent, all of a sudden this is partially negative. And that's because we've inserted the metal, which has a less electronegative value. So that makes the carbon more electronegative. And so what happens here is the electrons are pulled or withdrawn this way to give this a partial negative charge. Another way to say this is also kind of electropositive, right? So we can either say this is less electronegative or more electropositive, making this more electronegative. All right. Now, I also want you to notice here, shown on this slide, that the carbon atom, well, let me back up, that we could also look at how this reacts once we form a Grignard, okay? So we form the Grignard here. The Grignard is used in this reaction. This electron-rich carbon atom is going to be attracted to this partially positive carbon atom here. And remember, this is partially positive because this oxygen is electronegative, and so it's going to withdraw electron density here. And so that's why we're going to see an attraction there. And so we can see the new carbon-carbon bond formed here from this electro-rich carbon atom and the electron-poor carbon atom. Now, another example of an Umpolung. So Grignard's an Umpolung, right, where we're reversing the poles. But another example is the conversion of an alkyl halide into a Wittig reagent. So when we look at Wittig reagents, what we see here is that, and I just want to remind you, this was in chapter 18, so this is a bit of a review. So when we look at this, we have an electron-poor carbon atom here of an alkyl halide. And we use the triphenyl phosphine complex here and a lithium complex. And what we see here is that now there's an electron-rich carbon atom. Because again, notice there's a positive charge here. And so when we see this, right, this electron-rich carbon atom can react with this partially positive carbonyl group, and it can form the bond here, right? Now, this is not a stereospecific reaction, so it also forms the diastereomer. So a lot of times in your book, you're going to see and the diastereomer. And so basically, and remember, in this reaction, basically, this new carbon goes where the oxygen is, and it keeps that double bond there. But that's also an Umpolung. We've reversed the positions. Now, carbon-carbon bond-forming reactions are super important in organic synthesis because they let us alter the carbon framework. And in a lot of these reactions, heteroatoms in the product are left with very specific relative locations along the carbon skeleton. So the relative position of heteroatoms in a target can give us a clue about which carbon-carbon bond-forming reactions we might use in the synthesis. So, for example, in the formation of a cyanohydrin, which is shown here in equation 21.7, a carbon-carbon bond is formed between the cyanide carbon here and the carbonyl carbon here. Notice that the two heteroatoms in the product, the nitrogen here and the oxygen here, are attached to the carbon atoms that are adjacent to each other. Okay, so the OH is attached to the carbon in what we're going to consider the 1 position, and then the nitrogen's attached to the carbon in the 2 position. And so this is referred to as 1-2 positioning, okay, where they're here and here. So what we can say here and how we would describe this is using this sentence here. The heteroatoms are attached to adjacent carbons, so they are going to have 1-2 positioning. And I'm going to add, when we talk about 1-2 positioning, we can also add relative to each other along the carbon backbone. Okay, so let's look at how we can use this as a clue when we're looking for a synthesis. Okay, so let's look at this problem. So knowing that this reaction produces a compound with 1-2 positioning of the heteroatoms, that is useful when our target molecule is not a cyanohydrin. So this is, knowing this is useful when our target molecule is not a cyanohydrin, right? But still has heteroatoms with 1-2 positioning, right? So, for example, we want to carry out the following synthesis. We're given a ketone and we see that we have heteroatoms in the 1-2 position. So a few things we should note about this is this synthesis calls for a new carbon-carbon bond. Okay, and then we also need to notice the target has functional groups in a 1-2 position. I'm going to say in a 1-2 positioning. Okay. So now the nitrogen and oxygen atoms in this, and we have this 1-2 positioning along the carbon backbone. So we should consider a cyanohydrin as the synthetic intermediate. So look, okay, so when you see this kind of 1-2 positioning in your product, right, the clue there, right, the clue that we're looking for is that we should consider a cyanohydrin as a synthetic intermediate, right? And so when we look at this retrosynthetic analysis, what you can see here is the cyanohydrin leads to that 1-2 positioning, right? And we can undo a cyanohydrin formation. So when we look at this, we need to solve the conversion of the cyanohydrin into the target, okay? And so we need to convert the OH group. So let me show this. I think this will help. We need to convert the OH group to the ether, okay? So we need to convert this OH group here into the ether here, right? And convert the C triple bond N group right here and right here to a primary amine, okay? And so when we look at this reaction scheme, the OH can be converted, the OH that's right here, right, can be converted into an ether using that Williamson synthesis, right? And then the C triple bond N can be converted to a primary amine, right? So we're going to convert to a primary amine by reduction with that lithium aluminum hydride, okay? And so we can see how this would be a multi-step synthesis using several of the things that we've learned since we first went over multi-step synthesis. Now, cyanohydrin formation, which is what we're looking at here, is not the only carbon-carbon bond forming reaction that results in heteroatoms that have specific relative positioning. Okay, so if you look at table 21.1, this is going to show other reactions that we've looked at whose products have heteroatoms with 1, 2, 1, 3, and then on the next slide, 1, 4, and 1, 5 positioning. And I just broke this up over 2 slides just so we could look at it and make some comparisons. So when we look at this specifically, right, when you look at these tables, this is the product form. This shows you the electron-rich reactant, and this shows you the electron-poor reactant. And it also gives you an idea of where this was discussed, okay? So when we react a ketone or aldehyde with a cyanide anion, we get that cyanohydrin, and we form the new carbon-carbon bond here. And that's got the 1, 2 positioning that we talked about, right? 1, 2. Now, we can also get 1, 3 positioning with a, when we react a ketone and aldehyde with an enolate ion. And so we see here that 1, 2, 3 type positioning where relative to everything else around. So you have to understand this has nothing to do with the name of the molecule. It's a secondary internal counting, right? So notice there are all these R groups here. Okay, so this could be a big molecule, but what we're talking about is relative, the functional groups being relative to each other. So this would be 1, 2, 3, and that's a beta hydroxy ketone or aldehyde. Then, if we look at this table here, we see that there's 1, 4 positioning, right? Where if we take a cyanide anion and an alpha beta unsaturated ketone or aldehyde. And so I want to remind you here that we're going to see a double bond here and then a double bond here as well. And the way that this works is this is the alpha and that's the beta carbon, and unsaturated means there's a double bond there. And so we determine this as alpha because it's 1 over from this carbonyl carbon. So alpha and then beta. If there was another carbon, it'd be gamma, and so on through the Greek alphabet. And then here, and so when these two react, we end up with 1, 4 positioning. So 1, 2, 3, 4. Okay. So we've got the nitrogen on the 4th carbon and this oxygen here on the 1. Alternatively, you could also count 1, 2, 3, 4. There's nothing special about starting one from the other, just that the way the molecules, the heteroatoms fall. Now, we can also have 1, 5 positioning. And so we have an alpha beta unsaturated ketone or aldehyde. It reacts with an enolate ion. And what you see here is 1, 2, 3, 4, 5. So we have the 2 oxygen atoms there. I want you to notice, and I can't flip back because otherwise this will cut out, that in this chart, this goes, and on the previous slide, it goes cyanide anion, enolate anion. And then on the previous one, it's both a ketone and an aldehyde, and they give us those closer, the 1, 2, and 1, 3. And then here, it's that pattern repeats, cyanide anion and enolate anion, and this is an alpha-beta unsaturated ketone or aldehyde, and then with both of these. So we see these combinations of kind of the same reactants. Now, I have typed out some stuff here to kind of help us with just putting some words to what I've said. So if the heteroatoms in a target have the 1, 2, 1, 3, 1, 4, or 1, 5 positioning, like on this table, the synthesis calls for a carbon-carbon bond forming reaction, and you should consider using the corresponding reactions on this table, okay? If the functional groups in the target don't match the ones we produced from the carbon-carbon bond forming reaction, then consider implementing functional group transformations after the carbon-carbon has been formed. Okay, the important thing here is the after part. Okay, so not always, but by and far, right? You want to do the carbon-carbon bond formation and then the functional group transformation. Again, this is not an absolute rule. It's a really loose rule because every time we have a synthesis, it's a little different. But in general, this helps us avoid some synthetic traps. Again, just this is what I would consider first when I do a synthesis. Is there's a way to do a carbon-carbon bond formation before changing the functional groups. I try to do that. So let's look at some examples. Okay, so how should we synthesize 2-methylpentane 1,3-diol from a compound containing 5 or fewer carbons? Okay, and so like when we do other syntheses or other examples, I have some questions that you need to think about. And so the order of these questions is always really helpful. Will a carbon-carbon bond forming reaction be necessary? And so the way that you figure out if this is necessary is you need to count the carbons. So we know we're starting with 5 or fewer carbons, and then we come over here and we go, okay, hey, look, there's 1, 2, 3, 4, 5, 6, okay? So we have 6 carbons in the product. So we know that we need to use a carbon-carbon bond forming reaction because we're starting with 5 or fewer and there are 6 carbons in the product. So we're going to need a carbon-carbon bond forming reaction. Then what's the relative position of the heteroatoms in the target? So we notice that this target's got heteroatoms, right? We got 2 OH groups here. And so what we also notice here is these are in the 1 and the 3 positioning right here. So they're attached to the relative to each other. They're on the 1 and the first and the third carbon. Now understand, in this molecule they happen to be on the true first and the third carbon, but if there were more carbons off of it, they're just relative to each other on the 1 and the 3. Okay, so yes, it's a 1-3 positioning. Okay, and so should we consider a reaction from table 21.1? And so we go to our table, and on the previous slide, what we see, and it's actually 2 slides back, is for a 1 and 3 positioning, we should look at using an aldol reaction, okay? And so let's consider an aldol reaction where the product is a beta hydroxycarbonyl compound. Okay, so Now, is the target the same as the product of the carbon-carbon bond forming reaction? When we look at this, okay, and I'm gonna come down here to draw this out. This is our target. Okay, and what we're going to do here is we need, when we look at this aldol reaction from the 1,3 positioning, when you go back and you look at that table, what you're going to see, and specifically, is you're going to see for that aldol reaction, we're going to need, for the 1,3 positioning, we're going to need a carbonyl group and an alcohol group. So we're going to need that beta hydroxy ketone aldehyde. So we want to think about how do we go from this to that beta hydroxy ketone aldehyde. And the way to do that is to undo a hydride reduction. Okay, and so when we come here and do that, that would make that a double bond O. And we'd have an OH there. Okay, I was just counting my carbons to make sure I didn't create any other carbons. And now this intermediate here looks exactly like the 1,3 positioning that we learned in 19.7 that's shown 2 slides back, okay, where we have the carbon double bonded oxygen right here, and then the OH group right here, and they're in the 1 and 3 position relative to each other. Now, so the problem here is that we still have 6 carbons, right? So we've gotten our functional groups back, and so now we need to think about our carbon-carbon bond forming reaction. And since this target here is a 1,3 diol, and it can be made from the beta hydroxycarbonyl compound, and how we make that beta hydroxycarbonyl compound is we undo an aldol reaction. So you have to think back to the aldol reaction and say, okay, what are the precursors to that to make this? And so one of those would be 2, 3. This guy here, and then we could also react it like that, okay? And so when we, and this, what I did here really answers that question there, okay? And so when we applied that transform to undo the aldol reaction, we disconnected the bond between the carbon atoms that are alpha and beta to the carbonyl group, right? So we disconnected kind of that bond right there, okay? So the alpha and beta to the carbonyl group. So now we have to think, how do we report this final synthesis? And so we're going to look at it in the forward direction. So we look at it in the forward direction by saying, all right, and now we think and try to put together our reagents. And so to do this, we would need NaOH and NH4Cl and water. And then that would give us that molecule. And then we would come here and we would use sodium borohydride and ethanol as our solvent, and we would end up with that molecule. So this is a way where those positions of the heteroatoms help us with figuring out what reactants and what reactions we should use. Okay. Now, other things to consider. When we design a synthesis, we typically begin by looking for structural features in the target that suggest certain reactions. Right. And when we were in chapter 21, sorry, I had to stop the recording for a second, so because something was going on with animals again. So let me rephrase again. So we're going to look at structural features. And we have seen before in this screencast, chapter 21, that the reactions in table 21.1 that we just talked about can be incorporated into a synthesis when the target requires a carbon-carbon bond forming reaction that requires specific relative positions of heteroatoms. Okay. However, a lot of times a synthesis will call for a carbon-carbon bond forming reaction, but the target doesn't contain functional groups that suggest which carbon-carbon bond forming reaction we should use. And so if that's the case, the synthesis might be carried out by first forming the relative carbon-carbon bond and then removing a functional group to produce the target molecule. One reaction that removes a functional group is a catalytic hydrogenation of an alkene, which we learned in chapter 13, right? So we learned about this in chapter 13. Other reactions that remove a functional group are like the Wolff-Kishner. Reduction, which we learned in 1905, or the Clemenson reduction, which we learned in section 20.4, or the Rainey-Nickel reduction, which we learned about in section 20.4 as well. And so in each of these situations, the carbonyl group of a ketone, so we've got the carbonyl group of a ketone or an aldehyde is removed. Okay. Now, I want to emphasize, form the relative carbon-carbon bond forming reaction first, and then remove the functional group to produce the target molecule. A lot of times if you remove the functional group first, you lose all of the reactivity and you can't do any more reactions, because just honestly, these guys are pretty unreactive, right? If you don't have a functional group, if you just have a hydrocarbon, it's pretty unreactive. So try to wait until the end. So let's look at an example, okay? So we have propylbenzene. We want to synthesize it. We notice there's no functional group in the target molecule where we can have a carbon-carbon bond formation reaction should be used. But we notice we've got 6, 7, 8, 9. We've got 9 carbons in our product. So we have to use a carbon-carbon bond forming reaction, okay? And so because the backbone of the target has 9 carbons, we need to figure out what reaction we use to add carbons. The other kind of issue here is this target doesn't have any functional groups we would normally see in the product of a carbon-carbon bond forming reaction we've looked at so far. Okay, so no functional groups. So we don't quite have a hint of what we should do. Now, that being said, this is one of those kind of tricky situations where there could be multiple ways to synthesize this. There are multiple ways to synthesize this. And so we are going to try to find the best way to synthesize it, which a lot of times means the fewer steps, okay? Because that's just more cost effective. At this stage, you and your friend may do a synthesis like this and get different answers, but both of those answers be correct, as long as there are no synthetic traps. But if one has fewer steps, that's the better one to go with. But if they have the same number of steps, then we really need to kind of dig around into the cost of the reagents and things like that, which is outside the scope of this course. So, but I do want you to know that there could be multiple right answers to some of these questions before we get into solving this example. So let's look at this example. So we're going to try to form the carbon-carbon bond first in the reaction and then remove the functional group, okay? So thinking backwards, we need to put a functional group on that sucker and then, right, add the carbon-carbon bond, okay? So when we think backwards, put the functional group on, then remove the carbon-carbon bond, okay? So when we do this, we can get the target here from a ketone, right? If we alkylate the ketone's alpha carbon, okay? And so you can see where we undo an alpha alkylation here. So when we look at the forward reaction of that, okay, we have a functional group and we add the carbon to it, right, using an alpha alkylation. Then we remove the functional group to give a hydrocarbon, okay? So by and far, the big thing here is carbon-carbon bond formation first, then remove a functional group. It doesn't always work in every single instance, but most of the time it's the best way to go, because once you remove a functional group, you remove, so far, according to what we've learned, the reactivity, okay? So, as I mentioned before, there can be a couple ways to do this. Another way to do this would be, instead of converting this carbonyl group into a CH2 group, we could use catalytic hydrogenation to remove a carbon-carbon double bond. And so, look, here's an alternative one, right? Where we're going to undo a reduction, and so now we have this double-double bond, and then we undo a Wittig reaction, okay? So, again, when we think in reverse, right, we think like, okay, what functional group would I need to attach a carbon, okay? And how would I get that functional group? Okay, so we would undo reduction, and then we'd undo the Wittig. So in the forward reaction, right, we would take the alkyl halide, right? We would end up with an aldehyde here. Then we'd get a double bond, and then we would use hydrogenation to reduce that double bond. Both of these would be correct on a test, right? So know that there may be more than one way to solve these problems. Okay, let's do another example, okay? Here is a synthesis, right, where we are looking to make this product here, okay? And we need to start with a 6-carbon alpha beta unsaturated ketone or aldehyde. And we over here have 6, 7, 8 carbons, okay? So we know we're going to have to use a carbon-carbon bond reaction, okay? So when we think about this, one of the things that we need to ask ourselves is which carbon-carbon bond could be formed in the synthesis. Now, when we think about this, we could kind of cut this here, right? And that could be the carbon-carbon bond that's formed, okay? Because that would require a 6 and a 2 to give us an 8, okay? And we would still be within this 6 carbon, okay? And we could keep the ring together, and then we wouldn't need a ring opening or ring closing reaction. So it just incredibly simplifies the synthesis if we keep the ring together. Okay, so that's that. That would be what I would do. So this is a carbon-carbon. That's the carbon-carbon bond that can be formed. So then, thinking backwards, when that carbon-carbon bond is formed in the reaction, we know it's got to involve an alpha-beta unsaturated carbonyl compound. What functional group should appear in the product? Okay? And so when we think about this, we need to figure out, right, how to get this guy back to that alpha beta unsaturated ketone or aldehyde. And what we're really going to see is this is a ketone. So if we look at this reaction, and I'm going to just pop this down here, and we think through it, we are going to undo a reduction. Okay? And so, because we've got to get that ketone functional group back. And so if we undo a reduction, we could have a ketone here, and then we could add the carbon double bond using a conjugate addition. So then we would undo a conjugate addition. So we would end up with that guy there, and could react it with that carbanion. Okay? And so now we need to think about what reaction could generate that carbanion to attach. Okay, so now let's think in the forward direction. So when we do this, we're going to start with this guy. Okay, and one of the ways that you can get that carbanion two of them here, is to use the copper lithium, right? And I'm going to use THF as my solvent. That's just your solvent. And then we have to have the NH4Cl, okay? And we would synthesize that guy. And then we would remove that carbonyl compound there. Using this. Now remember, there's a lot of ways to do this, right? Okay. And so when we look at this, I specifically went with a Wolff-Kishner reduction here. You really shouldn't use a Clemenson. So that's a Wolff-Kishner, but I want to point out that you should avoid the Clemenson. Reduction because there's acidic conditions, and that would cause the C double bond C group to react. So if we use the Clemenson, this would have a reaction in the side product. So we want to avoid that. And then we also avoid Raney nickel. Right? Because it would reduce the carbon-carbon bond, right? So our issue here is we have two functional groups. We have a functional group here and a functional group here. And so we want to reduce this, but leave this one alone. And so the best way to do this is using the Wolff-Kishner, because both of these reactions would also react with this, okay? So lots of things to consider here. When you are thinking about organic synthesis, it is really, really helpful to remember all the reactions you've been taught. And so I'm sure this does not apply to any of you. But if maybe you have forgotten some reactions from previous chapters, it might be helpful to go back and review those. And the other thing you might want to look at is at the end of every chapter, there are lists of reactions that we've learned. And so you could even imagine from your book, you could photocopy those, or if you have the e-text, print those off, just that part, and put together a like notebook that's really a toolbox of reactions that you can use. And I think that would probably be really helpful as you work through some of these problems in this chapter. And of course, as always, you can come and ask questions.